A small and a large rock move through space. The smaller rock has mass 1.7 times 10 to the fourth kilograms, is initially at 47, -16, 20 meters, and has an initial velocity of -2.8, 1.2, -1.6 meters per second. The larger rock has mass 2.5 times 10 to the fifth kilograms, is initially at 32, 8, -7 meters, and has an initial velocity of -1.8, -0.4, 0.2 meters per second. Neglect the force of gravity throughout this problem. Will the rocks collide? If so, how long till the collision? Where will it take place? What is the initial position of the center of mass? What is the initial velocity of the center of mass? If the rocks collide and stick together, what is the final velocity of the combined mass? We can make a sketch of the possible collision, although this drawing obviously neglects motion along the z-axis. Our known quantities are the mass of the first rock, its initial position and its initial velocity, the mass of the second rock, its initial position and its initial velocity. The unknown quantities we wish to find are the position of the collision, the time until the collision, the initial position of the center of mass, the initial velocity of the center of mass, and the final velocity of the combined masses. First, we must check that the rocks do, in fact, collide. Since the rocks are drifting through space, and we are neglecting the force of gravity for this problem, we know that the net force acting on both of the rocks is 0. This means that they will move with constant velocity. Under constant velocity, we know that the change in position is equal to the velocity times the change in time. This tells us that R final equals V delta t plus R initial. We want to check that there is some delta t for which the two rocks are in the same place, or R final 1 equals R final 2. Thus we have V1 delta t plus R1 initial equals V2 delta t plus R2 initial. Rearranging this and factoring out the delta t, we have V1 initial minus V2 initial all times delta t is equal to R2 initial minus R1 initial. Since we have a difference of vectors on each side of the equation, we know that for the rocks to collide, R2 initial minus R1 initial must be a scalar multiple of V1 initial minus V2 initial. If this condition holds, these two vector differences will have the same unit vector. We calculate the unit vector for the difference in velocities as V1 initial minus V2 initial over the magnitude of V1 initial minus V2 initial. This gives us -2.8, 1.2, -1.6 meters per second, minus -1.8, -0.4, 0.2 meters per second, all over the square root of 1.0 meters per second squared plus 1.6 meters per second squared plus 1.8 meters per second squared. This gives us the unit vector -0.38, 0.61, -0.69. We can carry out the same calculation for the position vectors. R2 initial minus R1 initial all over the magnitude of R2 initial minus R1 initial is given by 32, 8, -7 meters minus 47, -16, 20 meters all over the square root of 15 meters squared plus 24 meters squared plus 27 meters squared. This yields the unit vector -0.38, 0.61, -0.69. Since the unit vectors match, we know that R2 initial minus R1 initial is in fact a scalar multiple of V1 initial minus V2 initial. This tells us that there is some delta t such that the rocks will eventually have the same position or collide. Since we confirmed that the unit vectors are the same, we can solve for the time until the collision by splitting the vector equation into components and just dealing with one component. In this case, I will choose the x component. Then, delta t collision is given by r2 initial x minus r1 initial x over v1 initial x minus v2 initial x, which gives us negative 15 meters over 1.0 meters per second. Thus, the time until the collision is 15 seconds. We can then find the position of the collision by plugging this delta t into either v1 initial delta t plus r1 initial or v2 initial delta t plus r2 initial. Using the first option, we have negative 2.8, 1.2, negative 1.6 meters per second times 15 seconds plus 47, negative 16, 20 meters. This gives us a position of 5.0, 2.0, negative 4.0 meters. Using the second option gives us negative 1.8, negative 0.4, 0.2 meters per second times 15 seconds plus 32, 8, negative 7 meters, which gives us the same answer of 5.0, 2.0, negative 4.0 meters. Next, we will find the initial position of the center of mass. The initial position of the center of mass is given by m1 r1 initial plus m2 r2 initial over m1 plus m2. This is 1.7 times 10 to the 4th kilograms times 47, negative 16, 20 meters plus 2.5 times 10 to the 5th kilograms times 32, 8, negative 7 meters, all over 1.7 times 10 to the 4th kilograms plus 2.5 times 10 to the 5th kilograms. This gives us 8.80, 1.73, negative 1.41, all times 10 to the 6th kilograms times meters, all over 2.67 times 10 to the 5th kilograms. Thus, the initial position of the center of mass is 33, 6.5, negative 5.3 meters. This answer makes sense because it is between R1 initial and R2 initial, but closer to R2 initial, which is the position of the greater mass. Next, we will calculate the initial velocity of the center of mass. This formula is very similar to that for the position of the center of mass. We will calculate the initial velocity of the center of mass using m1 v1 initial plus m2 v2 initial all over m1 plus m2. This is 1.7 times 10 to the 4th kilograms times negative 2.8, 1.2, negative 1.6 meters per second plus 2.5 times 10 to the 5th kilograms times negative 1.8, negative 0.4, 0.2 meters per second, all over 2.67 times 10 to the 5th kilograms. This yields negative 1.86, negative 0.30, negative 0.085 meters per second. This answer makes sense because it is closer to v2 initial, the velocity of the greater mass. Lastly, we will calculate the final velocity of the combined mass. We know that the net force on either mass is 0. This means that our momentum principle becomes delta P equals 0, or momentum is conserved. We know that the final momentum is then equal to the initial momentum, or the quantity m1 plus m2 times v1 v12 final is equal to m1 v1 initial plus m2 v2 initial. Dividing both sides by the sum of the two masses gives us v12 final is equal to m1 v1 initial plus m2 v2 initial over m1 plus m2. This is, of course, just the formula for center of mass velocity again. As we expect, since when no forces act on the system, the center of mass velocity should not change. Thus, the final velocity of the combined masses is just negative 1.86, negative 0.30, 0.085 meters per second. Reviewing our answers, we see that we found that the rocks will collide, they will collide 15 seconds in the future, and they will collide at 5.0, 2.0, negative 4.0 meters. The initial position of the center of mass is 33, 6.5, negative 5.3 meters, and the initial velocity of the center of mass is negative 1.86, negative 0.30, 0.085 meters per second, which is also the final velocity of the combined masses.